Last time we talked about the components of the circuit: source, the conducting wire or the path that the electrons follow, and the load that converts electric potential energy into some other type of useful energy. And today we're going to get a little bit more deep into how exactly a circuit works. So, we're going to start off with Kirchhoff's second law, which says that the total potential increase in a circuit has to be equal to the total potential decrease in a circuit. So that's a little bit difficult to understand just reading that, but let me tell you what it means. So, we've got a simple circuit over here. Here is our voltage source, a battery in this case, and here is our load. So, in a battery, you have a negative pole and a positive pole. Let's look at the negative pole. Let's just say we're talking about it pushing electrons out. So when we're talking about current flow in physics, yes, we are talking about the flow of positive charge, but it turns out that when we're talking about a circuit and doing the math involved in a circuit, it doesn't really matter whether you're talking about the flow of positive or negative charge. We can consider the entire circuit as just being full of current or full of electricity when you close that circuit. And when you open it, it is empty of electricity. Doesn't really matter which direction it's flowing. So that's how we're going to think about it. So let's look at the negative pole over here. It's pushing electrons out of it this way, but again, it doesn't really matter what direction we're talking about. At this point, right over here, those electrons have maximum potential energy, right? At this point is the spot of maximum potential in the circuit. That's because electrons will experience the most force right over here pushing it out of the battery. By the time it goes all the way around the circuit, right here is the spot of lowest potential, the lowest voltage. Okay? And that makes sense because an electron, once it reaches this spot, has nowhere else to go. This is as far as it can fall if we're talking about a gravity type thing. So electrons have the most potential energy at the negative pole, and then they will go around the circuit, lose potential energy as they go, because by the time they make it to the positive pole, they have to have zero potential energy. And that's why it's important that there's some sort of load in the circuit, some way for them to lose potential energy. Okay? So, we have a voltage drop occurring throughout this circuit. Yes, the electrons will lose a little bit of potential energy as they move through the wire itself. The wire itself will use up some of that electric potential energy, but it's almost negligible, especially if you're using a good conductor. A good conductor just has very, very little resistance. And so we can consider that this resistor over here will use up all of the electric potential energy. Okay? The electrons will still travel the rest of the way because the wire does provide a little bit of resistance, a little bit of using up of electric potential energy, but we can just consider it as negligible. Okay, so let's say that this battery is a 3-volt battery. You'll see that a bunch of times in different types of batteries, especially button cell batteries, those little flat round ones, they often have 3 volts. Or if you stack 2 AA batteries, then you'll get a voltage of 3 volts as well. So, 3 volts is given to the electrons as they're going to travel through this circuit. Across this resistor then, there must be a drop of 3 volts. This resistor will use up 3 volts of potential. Now, you don't really use up potential, but we can think of it that way as well. So this is adding 3 volts to the circuit, and this is subtracting 3 volts from a circuit. Okay? Now, if we look over here in this other part, it's got 2 resistors. So right here on the positive pole, you've got a voltage of 0 volts. Right? Because this is the resting place for electrons. On the other side, the negative pole, you have 4 volts of potential. So electrons here will be given potential energy, and then they will move through the circuit as they're repelled from this negative pole, and as they pass through the components in the circuit, that electric potential energy they had will be converted to some other form. And in this resistor, we're going from 4 volts down to 1 volt, so that's a drop of 3 volts. And then those electrons will still have some energy as they come out of this end of the resistor, and then they'll enter this resistor and they'll drop another 1 volt. The rest of the voltage must be dropped through this resistor because there are no other components here. And so the electrons will just move from here to here because of that tiny amount of resistance they'll get from the wire itself. We have to remember then that the amount of current in any location is going to be the same. Okay, current is the flow of electrons. So it's not like electrons are disappearing when they travel through this resistor. Their energy is being used up, being turned into something else. The electrons are still there. So the amount of voltage is decreasing as you pass through the circuit, but the amount of current is not. The amount of current is staying the same. Now that is for circuits that only have a single path to follow. Many circuits have multiple paths to follow, and then the current is not the same in each portion of the circuit. That depends on how much resistance there is in each portion of the circuit. Those are called parallel circuits. We'll get to those a little bit later. Today we're talking about series circuits. Series circuits are the circuits that only have one path for electricity to follow. That brings us to Ohm's law, which is the relationship between voltage, current, and resistance in any circuit. Series circuits, parallel circuits, it all works. So what this says, V equals IR, is that the amount of voltage depends on the current and resistance in the circuit. Or you can think of it a different way. Let's say that we have 4 volts coming from this battery. So the battery provides 4 volts of potential for the electrons. Okay, if we would increase the amount of resistance in the circuit, so let's say we make this resistor twice as big, that means less current is going to flow. Okay, so if we had 4 volts here, and then this resistance got bigger, the current would have to get smaller to accommodate that resistance change. Let's throw some numbers in and see what happens here. So let's go with this simple circuit over here. We've got 3 volts. That's the potential difference for the circuit. Let's say that this resistor is 10 ohms. That's the symbol for ohms. It's the letter omega. So 3 volts is our potential difference. The current, I'm going to just leave it as I, and then our resistance is 10 ohms. Okay, so then if I divide by 10, then I get my current is 0.3 amps. Okay, but let's say now, instead of 10 ohms, I make this, let's just do it in red, I make this 20 ohms. I'm doubling the amount of resistance. So now if we do the math, 3 volts is equal to I times 20 ohms. Now if I take 3 and divide it by 20, I end up with 0.15 amps is the current. So if I double the current, or if I double the resistance, I have the amount of current. Double the resistance cuts the current in half. It works that way for anything. If I increase the amount of voltage, then the amount of current is going to go up if the resistance stays the same. We're going to do some examples of that in a moment. A flashlight has a 3-volt battery and has a current of 0.4 amps as shown below. What is the resistance of the light? So we can use Ohm's law to calculate all sorts of things like this. Voltage equals current times resistance. So it tells us that the voltage is 3 volts, and the current is 0.4 amps. And so we're looking for what's the resistance? Okay, and so when we do that, divide by 0.4, you get 7.5 ohms. So the resistance is 7.5 ohms. Now, you can just solve circuits like this to figure out what's going on, but this matters the most for people who are actually building electronics, building components for something. They need to select the right components in order to make the circuit work properly. So you can't just throw a flashlight, connect it to a battery, and it work. It's not going to work properly. You need to make sure that you have the right light bulb connected to the right battery with the right resistors in the mix as well. Two resistors are connected in series as shown below. What is the resistance of R2? We're going to use the same strategy as before. So we know the total voltage, we know the total current, and so we should be able to find the total resistance. Now the total resistance for a circuit like this is just all the resistors added up. So we can use V equals IR to do the exact same thing we did before. 4.5 volts is 0.75 amps times the total resistance. So the thing with V equals IR is that you have to match what components you're talking about. So we're using the total voltage, the total current, and so that will give us the total resistance. It won't give us R2. If we wanted to directly calculate R2, we would have to know the voltage drop for this particular resistor individually. We would have to know the current through this resistor individually, and that means we could directly calculate what R2 was. And that works totally fine, except that we don't know the voltage drop for this one. We could figure it out, but we'll look at that later. So if I divide 4.5 by 0.75, I get 6. 6 ohms is the resistance, but that's the total resistance, not R2. But I know that R1 is 4 ohms, and so R2 must be 2 ohms, right? The two of them have to add up to 6 ohms altogether, and so I know that R2 must be 2 ohms, because 4 plus 6 is 2. And that brings us to equivalent resistance of circuits. By equivalent resistance, we mean just the total resistance of the circuit. Okay, but you can also consider equivalent resistances of pieces of the circuit. So what that means is if you would take multiple components or multiple resistors and kind of stuff them into one, you're just combining them into one resistor, that would be called the equivalent resistance of some section of the circuit. Very often we'll talk about equivalent resistance of the entire circuit, so that just means total resistance, but sometimes we'll need to look at the equivalent resistance of certain sections of a circuit. Okay, and in a series circuit, or in a series component of a circuit, you have a very simple relationship. You just add up all the resistances, and that gives you the total resistance of the circuit. So, for instance, let's calculate Req, or the equivalent resistance of this little circuit here. It's 2 plus 3. It's 5 ohms. Okay, that's a series circuit. It's just adding up the resistors. But in some instances, you'll need to use equivalent resistance in order to solve some other portion of the circuit. So it's not always just about adding up resistors and finding the total resistance. Sometimes it's a piece of a larger puzzle. So let's look at this circuit here. We've got total voltage not told to us. R2 equals, don't know, not told to us. But we do know that resistor 2 uses up 5 volts of potential. We're also not told the total current going through the circuit, but we do know that the current going through R2 is the same as the current going through R1, because all of the electrons that come out of the battery have to pass through every component in order to get back here. There's no alternate path to take. And we also know the resistance of R1 and how much voltage it drops. Okay, and so we can fill in some other things here. we can find the total potential increase of the source. And we can do that because we know that all of the individual voltage drops have to add up to the total. So the total voltage supplied at the source is 15 volts plus 5 volts. So Vt is V1 plus V2. And so the total voltage in the circuit is going to be 20 volts. Okay, so we already know one piece. Find the current through R1. R1 is over here. We don't know the current in the circuit, but because we know the resistance of R1 and the voltage of R1, we can use V equals IR. We can use Ohm's law for that particular component. So we would be using V1 equals I1 times R1. Ohm's law is going to be really useful for solving all sorts of components in circuits. So we know that V1 is 15 volts. That's the amount of potential that's used by that resistor. We don't know the current, but we're going to solve for that. And we know R1 is 5 ohms. And so we're going to figure out the current by taking 15 volts divided by 5 ohms. So the current through resistor 1, we call that I1, is equal to 3 amps. Okay. We also know that any current that travels through R1 in a series circuit also has to travel through R2. None of the electrons are disappearing. All of those electrons have to pass through R2. And so the current through R2, this piece over here, is also going to be 3 amps. Because I1 has to equal I2. Let me try that again. I2. And that is 3 amps. So the current through resistor 2 is also going to be 3 amps. That's going to allow us to find the value of R2. So the value of R2 can be figured out using V equals IR again, because now we have V2 is told to us, I2 we also have now, and so now we can solve for R2. Okay, so V2 is going to be 5 volts I2 is 3 amps. And we can solve for R2. So 5 volts divided by 3 amps, R2. 1.67, or 1 2/3. 1.67 ohms. The final piece here is calculating the equivalent resistance of the circuit. So we know that resistor 1 is 5 ohms. We now know that resistor 2 is 1.67 ohms. And so altogether, those two resistors are going to be just adding those two up. Okay, so Req for this circuit is 5 ohms. That's R1. Plus 1.67 ohms. That's R2. And so the total is 6.67 ohms. So we see in this example that we needed to use multiple ideas, multiple concepts to solve for all of the pieces in the circuit. It's like a puzzle that we're adding tools to for the entire time. And what we're looking forward to is solving combination circuits. So they're going to be series components, there are going to be parallel components. And so we're going to put together this toolbox of problem-solving techniques so that we can solve any circuit. In this circuit, we had to recognize several things. That current is the same through each series resistor. We had to recognize that the voltage drop for all of the individual components equals the total voltage increase. That's Kirchhoff's second law. And we also had to use Ohm's law several times. So we had to use 3 different tools in order to solve this simple circuit. And you're going to get used to using those tools, but you do have to recognize what you need to use for any component. So it's important to do the practice.